Okay, so welcome to this first lecture in numerics in the CFD course. As I was saying before, the first 3-4 hours, so maybe this week, we will talk about topics that are kind of basic to numerics and not specifically for CFD. And then afterwards, we will look at problems that are actually problems that may appear in fluid mechanics or kind of energy related scientific questions or engineering questions. So, but the first part is a selection of topics that I think is it's kind of relevant for us to understand how numerics works. Also, what maybe the critical aspects are in terms of, you know, what happens if something blows up, what happens if you see wiggles, or if something doesn't look right, what could be the sources of that. And therefore, I chose these initial topics in such a way that it's necessary or it's helpful for us. I know in particular the first lecture, the one today, may sound a little bit mathematical at times, but yet I still think the outcome of it is actually relevant for us to understand how things work. So therefore, please bear with me also, you know, through the lecture today. But kind of the actual start for today is kind of a more philosophical way. I would like to discuss very briefly of how to actually approach a fluid mechanics problem. Very simply. So let me start like this. So basic numerics. And we start with the first lecture today. So let's just talk about, you know, the different steps that you need to do if you want to solve fluid mechanics or a CFD problem. So of course, the first step typically is you actually need to understand what is it really that you want to solve? What is the problem that you would like to look at? Of course, this sounds very, very trivial, but yet you need to kind of think about it. What is it really? So what is the physical problem that you would like to address? And of course, this means, you know, what is the geometry? What is the inflow? You know, stuff like that. And of course, you typically are guided by some experience. You have some experiments maybe in mind that you would like to replicate, or you have a kind of a specific problem in your, you know, your engine or your I don't know, your aerodynamics that you would like to address. But the first thing is always define the problem. And if I would like to make a sketch now, that's essentially, you know, defining maybe a wing. So you would kind of say, I would like to study this wing, this particular shape of the wing. Okay. The second step then, always after you have defined the physical problem with all the whole range of physical difficulties, you kind of need to make an idealization of that. So you need to come up with a physical model. A physical model that you would actually like to look at. And what does that mean? Well, there's certain approximations. And these approximations, they could be related maybe to the, you know, the shape of the surface or the surface finish. You know, is it a flat plate? Is it a rough surface? It's about what equations to use. So equations to use. So for instance, what is the density? What is, I don't know, the viscosity? What is the Mach number? And so on. So that means, well, what we need to define in the second step somehow is we need to define the flow. We need with the viscosity, with the Mach number, and so on. And I would say this is kind of still part of the physical model. That's before you do any CFD, you kind of need to come up with this. The third step then is you need to go from the physical model into kind of a mathematical description of this. I would say you can say that this is the mathematical model that is then underlying the physical model. And that means essentially to come up with a mathematical description of your problem. So writing down partial differential equations, defining boundary conditions, you know, no slip boundary conditions, for instance, or rough wall boundary conditions. It's defining inflows and all of these type of things. So if I go back to my little sketch here, it would mean that I would need to define a partial differential equation. I need to define the boundary conditions on the surface, for instance. I also, at this stage, I would need to kind of truncate my domain. I would say, okay, I will actually look at a box, maybe that looks like this, and with my mathematical modeling, I can say that I for instance, replace the boundary conditions on this side, perhaps with a symmetry boundary condition down here. I would add an outflow boundary condition, a non-reflective condition, or I would have an inflow condition at this side. Okay, so I have now my mathematical model, but yet I'm still not able to kind of run it on a computer. So the fourth step, if you now think of CFD, would be to do a so-called discretization. So essentially, the idea is now go from the mathematical model into a language that a computer can understand. And that means discretization. So I need to, in a nutshell, I need to replace all the partial derivatives with ways that the computer can calculate. And that essentially is, we need to go into an algebraic system of equations, a linear system, maybe a nonlinear system, but somehow into a system of equations. And of course, there's a lot of questions here, and some of them we will address during the course, namely what methods to use is kind of the question here. So what method to discretize, and that could be then finite differences, for instance. Finite differences, finite element, finite volume, all these type of things can be answered in step number 4. For the kind of my sketch, it would mean that I go from the partial differential equation, so from a continuous formulation into a discretized form. So that would mean maybe I would put a computational mesh. I would only calculate the solution in discrete grid points, and I would find relations of how to relate these grid points with each other. At that stage, once I have done this, I can actually start to sit on the computer. Up to this point, all of this has been analytical work. So I've not yet programmed anything. So step number 5 is then to actually implement the solution scheme. So for instance, implement the method to solve a system of equations. I don't know, an LU decomposition or a GMRS or whatever method you would like to solve an equation. And of course, this now needs to be programmed in a computer. So that is then when I sit and actually do programming in a computer. Once I have programmed it, then of course at some point I have done that and I need to do a calculation. And of course this calculation can be done on a laptop, this can be done on a workstation under your desk, or it can be done on a supercomputer with thousands or millions or whatever number of processors. And this calculation may be overnight, it may be a few weeks that the computer runs, or it can be a few months that you have for a single calculation. But then, once I have done the calculation and I have a solution, then perhaps comes, well, not the most important step, but a step that is of course very, very relevant in all of these things, and that is the validation step. I need to look at the errors that I have done. Some errors I know. Maybe I have a certain grid resolution, so I know that in certain regions my grid was not very good, so I might have a lot of errors. Some other errors I do not know. So for instance, typically if I want to reproduce an experiment, I do not know all the details of the experiment, so I don't know what turbulence intensity they had. I don't know exactly what geometry they were using. These type of things are errors which I don't know, but yet I need to come up with an estimate of how good or how bad this was. And of course, I also need to look at the results. So I need to do some sort of post-processing in a sense of analyzing my data, extracting mean values or profiles, whatever is needed, coherent structures perhaps, and so on. And of course, at this stage, at the validation step, it's of course important to then actually check whether what I have done in the beginning, namely when I chose the physical problem or when I chose the physical model, whether these choices were actually correct. So for instance, I mean, a very simple example, but it's kind of explaining the idea here. I mean, if I've calculated in the beginning or estimated in the beginning my Mach number to be maybe 0.1, and common sense says that if the Mach number is so low, maybe an incompressible approximation would be sufficient. But then I have done the solution, or I've calculated everything, I got the solution, and I realized, my Mach number was actually 0.9. Then I guess it would come the point when you have to say, okay, maybe the choice of doing incompressible simulations was not a very good choice. I actually should have chosen a compressible simulation, or the compressible equations, for instance. Similarly, my mathematical models, the choice of the boundary conditions may not be correct. Maybe the outflow was not as non-reflective as I thought it was, or finite difference schemes were not of enough high accuracy or sufficient accuracy, etc. But the important step here is that at the validation step, I really need to go back to all the steps that I have talked about before and assess whether or not these choices have been correct. So in that sense, you should maybe not think of doing CFD as a strictly linear problem where you start with a problem and then you end up with a solution. It is much more intertwined, and you need to go back and forth all the time, maybe making certain changes in the methods, in the boundary conditions as you go along. Somehow, I mean, it sounds a little bit corny, but my professor a long time ago, when I studied CFD, he was always saying that CFD is really an art to perform, because you need to understand so many effects or things that may affect the solution, and you need to directly know, okay, if this happens, then maybe it was caused by that. So it's really a coupled problem, more like an artwork than just kind of an engineering problem. Now, I wrote this down as kind of as some guidelines. There is in fact people that have studied on a more theoretical levels exactly these interactions. And I just want to paste here. Of course, it doesn't. Oh no, it works. I would like to paste here this particular slide that I took from a presentation, which to some extent summarizes in slightly different words, but a kind of the same complex interaction between different sources of errors and different, mathematical or numerical modelings is expressed here. In particular, I think it's what I like from this slide, which you don't go in all detail, but I think the two concepts of verification and validation within CFD are very important. And in short, validation and verification have two different meanings. So verification is essentially related to the fact whether or not I have implemented my simulation method in the correct way. So that means in my discussion here, whether the solution scheme is actually what I had in my mathematical model, whereas the validation step, which is written here, is about whether or not my calculation actually is doing the right thing. So these are two important aspects which one always needs to take into account when considering CFD solutions. So the concept of verification and validation. And if both of them are kind of performed well, then you know that you have done a correct result for your, or that you have obtained a correct result for your simulation. But as you can also see on this slide, there's of course a lot of different uncertainties and errors that may come in at various stages of the problem. And it's all about kind of knowing where they are and being able to handle them in the best possible way. Another aspect that I would very briefly like to mention is the aspect of calculating the solution. So step number 6, and I would like to mention what I call here top 500. That is a list that is available on the internet, and I will just copy it here as well, so that you can see that. So this here, this diagram is the so-called top 500 list. What does this have to do with what we talk about here? So the top 500 list is a list of the 500 fastest computers every half year. So this list will be updated every 6 months. And it essentially shows, as a function of year, here it goes from 1990 until 2020, it shows how the speed of the fastest computers have evolved during the last decades. And what you can see here is that the yellow one, that's number 1. This one here is the computer with rank 500 on the list, and the green one is the sum of the performance of all the computers. And the performance is measured, just write it down, so this is this is badly written, performance. So this performance is measured in teraflop, meaning 10 to the 12 floating point operations per second. So this is kind of the measure of how fast the computer calculates these days. The important thing here is what you can directly see is that these curves are all exponentially growing up to maybe here at the end, where there's kind of a slight leveling off to be detected, which means that the computer time essentially doubles, or the computer performance essentially doubles every 18 months. And as you know, or may know, this is what is called the Moore's law. Moore was a computer scientist, which then became also the founder, one of the founders of Intel, who postulated that in the 60s, that the number of transistors on a chip essentially doubles every 18 months. And of course, this is good news for us, because we know that within 18 months, our computer will be twice as fast. And of course, that means that somehow the simulation can be twice as fast, twice as big in 1.5 years, and it will still only take the same amount of time. Of course, it's not exactly true, but it gives us kind of an idea. Another interesting aspect, and that's kind of the last thing before we then really dive into the mathematical part of this lecture, is kind of to see, this is the top 500 list with a lot of very good computers. But where would now be my mobile phone? Now you don't see it. So where would be my mobile phone on this list? Well, it turns out that an iPhone 11, so if I take an iPhone 11, so that's from 2019, I think, that has a performance of roughly 1.5 gigaflops. So that means the iPhone, just one iPhone, would actually be around here. So that's that's the iPhone. And now, of course, the cool thing is, if you now just go, back, you see here that in 1995, one iPhone would have been the 500 or number 500 in the top 500 list. It would be the 500th fastest computer in the world. Just one iPhone. And of course, that's kind of a scary thought, because I mean, in the same way, it will continue for the future. In 20 years, the iPhones that people will have in 20 years would be as fast as the biggest supercomputer that is, standing somewhere in a big room. Of course, that means also for us doing CFD, we work in an area where methods and programming languages evolve extremely fast, and we always need to adapt our methods to this fast development. I mean, one thing you're certainly aware of is the idea of machine learning, which has kind of come into all fields of science these days. And of course, these are things that were very recently, developed. And we, of course, need to adapt our methods to kind of take advantage of all these new technologies. But yet again, and this is also what I would like to say before we now go into the other topic, yet again, there is a few basic things in numerics that we just need to understand before we can really jump into these very modern technologies. A few things, a few very basic aspects of numerics, they are the same, and we still need to understand them. Therefore, I also think that maybe the first few lectures can actually can be considered quite basic in that regard. Okay, with this, I would kind of like to leave this introductory part and dive into the mathematics of CFD. And well, or maybe there are some questions or something that you would like to discuss right now. If not, then now let's start with the mathematical description. And essentially, I have three parts: A, B, and C that I will go through. And part A is about model equations and classification. So that's where we would like to start. The reason why we would like to look at model equations and in particular classification is that it actually turns out that the solution to different types of problems behave very differently. So solutions, numerical solutions, or actually also analytical solutions to different types of problems. And with different types of problems, I mean mathematical types in the sense of the mathematical properties of the equations. So we will in a second see what I mean with that. But it's kind of a mathematical characterization or classification of problems, and they behave very differently. And this, of course, directly means that the choice of the numerical method depends on these characteristics or properties, let's say. Let me just give one example here. So if you think of supersonic flow, so high-speed flow, there's a lot of shocks that may appear in the flow. And of course, if you have a shock appearing in a flow, you need to have a numerical method that is actually able to deal with shocks. So that you will not get instabilities in the whole domain when you have a discontinuity in one place. And so, for instance, global spectral methods would not be appropriate for flows with a shock. And of course, this you need to know before you make the a prudent choice of what method to use. But it's not just the numerical method that matters. It's actually, and that's maybe even more important, it's the number, type, and location of boundary conditions. Of boundary conditions depends on the type of equation. Also here, maybe just a brief example, if you have hypersonic flow, typically you would not use need an outflow boundary conditions because everything is kind of convecting out anyway. On the other hand, if you have a well-behaved, I don't know, a Laplace type of problem where you solve a Laplace or a Poisson equation, of course you need to have boundary conditions everywhere for it to be to give a correct solution. So therefore, it's very important that we understand what mathematical problem we're actually solving. Let me start with the first definition that we're going to use, and that is the definition of the concept of well-posedness, or the definition of whether a problem is actually well posed. And that goes back to Hadamard. And that was written up in a paper in 1902, so roughly maybe 100, 120 years ago. And why I'm also mentioning here the year is kind of the idea of that all these concepts that we discuss within CFD or numerics in general, they're typically 100 years old. It's not much more, because it was only at that point that people understood that you could actually do numerical solutions to analytical problems. Before, mathematics was mainly about finding closed form solutions. But maybe during the last century, it became clear that at times you can also use computers to do that. So this goes back to Hadamard, and it's actually a very simple definition. And it's as follows. So a system of partial differential equations together with their initial conditions and boundary conditions constitute a well-posed problem if, and there's essentially three conditions. A, or one, if there is a solution, so if a solution exists. B, this solution is unique. And third, that the solution depends continuously on the initial conditions and boundary conditions. That is essentially when we talk about a well-posed problem. Now, the relevance of this, I come back to the individual points in a second, but the relevance of this is that a solution to a not well-posed problem or a ill-posed problem does in general not make sense and should not be attempted. Of course, there's exceptions to that. Should not be attempted. I mean, there's exceptions here, which then kind of goes into the idea of regression or inverse problems, where the whole idea is that you have an ill-posed problems. But in those cases, you typically need to add some regularization to the problem to make a solution worthwhile anyway. But for typical physical problems, you need to make sure that your system composing of the equations and the initial and boundary conditions is actually well posed. One simple example of a problem that is not well posed is the following, which we call the backward heat equation, kind of the classical example here, that would look like this. So du dt is the same as minus nu times d squared u dx squared. And this is ill-posed if this nu parameter is larger than 0. For those that have seen this type of problems before, I can say a few words. For the others, I guess very soon we will discuss the heat equation in more detail. But the basic idea here is that this would correspond to the spreading of heat, but we have added a minus sign in front of the diffusion coefficient or the heat coefficient, or the diffusive coefficient here, which means that instead of spreading out, it would actually do the opposite. That's why it's called the backward heat equation. And the resulting solution here is that essentially what you will get is an amplification of small scale of errors. And this here would validate number 3 of our list here, namely that the solution depends continuously on initial and boundary conditions, because it would just amplify errors in these conditions, but it would not depend in a meaningful way on the initial and boundary conditions. It would just amplify errors in the solution. But to come back to the 3 points here, so why or when a system is well posed, well, I guess the first 2 points, they make kind of intuitively sense. It means that we need to formulate the problem in such a way that we can actually get a solution. And if one is a mathematician, one would need to prove that, that there is a solution, and in particular also that the solution is unique. For us as an engineer, of course, it's a slightly different situation, particularly also because showing this is very difficult for nonlinear problems like the Navier-Stokes equations. And typically there is not even an existence or uniqueness proof available for Navier-Stokes. Only for very specific cases there is a proof. But for us as an engineer, perhaps it's sufficient to know that there is a solution because we know it from kind of the physical view on the problem. But of course, for a mathematician, this would not be sufficient. Okay, but this is kind of the first important aspect of CFD. We need to make sure that the problem we pose is actually well posed. If it is not, then we don't even need to try to do that. Or we need to change the problem such that it becomes well posed. Okay, but with this, let's now dive into classification. Classification of PDEs. Okay, so let's consider kind of a very abstract way. In a very abstract way, we consider a system of linear first order partial differential equations in 2 variables, x and y, with let's say with n unknowns. And these unknowns are u1, u2, up to un. Of course, this we can write like this: a times du dx plus b times du dy is c. So this is kind of the general way how I could write a system of linear first order partial differential equations. Now, of course, here I need to introduce a little bit of notation. I would now write an underline under u if I talk about a vector. So we can say that this is the u vector. And I can make 2 lines under A and B to indicate that this would correspond to a matrix. Of course, then on the right-hand side, I will also have a vector. So it's a matrix A multiplied with the derivative in x plus a matrix times the derivative in y equaling a vector C. Okay. Now I would like to determine the type of this equation. And now in order to do that, I do the following. Assume a curve in x and y. I can say that this curve can be written like this, f of x and y being 0. So in the x and y plane, with a specific parameterization S. So that simply means I have x for this curve. I have x is x of s, and I have y being y of s. So if I just make a sketch of this, I have x, I have y, and I have a curve in here. This is my curve f, and I have a parameterization along the curve S. As simple as that. Okay. Now, I would like to calculate my derivative of u. So u is a function of x and y. So u exists in this plane. So the derivative with respect to s. So what is the change of u as I go along the curve? So du ds. What is that? Well, so I would like to have the derivative with respect to s. And of course, s depends on x and y. So what I'm actually doing is I'm calculating a total derivative. So, I mean, essentially, I need to use the chain rule in this case. So that means this will be du dx times dx ds plus du dy times dy ds. Okay. Notice here that that these are partial derivatives and these are normal derivatives. Okay. So far so good. So there was nothing very strange here. I just did this derivative. But now the next step would be, okay, I can simplify this. Let me just go in and say that the parameterization along x or s is essentially x. So instead of s, I can use x. So I'll just use this as the parameterization. I just go from left to right. And that makes it a little bit simpler because then I can write like this, that du dx. And now we need to say that I'm actually moving along the curve f. And I just take the same derivative, the same total derivative, just knowing that dx ds is 1. It gives du dx plus dy dx along the curve f times du dy. Okay. Now, so I have this equation plus I have my original partial differential equation in equation number 1. And I can combine these two equations. So system 1 becomes, when eliminating this du dx term, actually it's the du dx term. So I eliminate, no, it's the partial derivative, of course, what I'm doing. So it's this. So it's this term, and I eliminate it together with this term. Well, what do I get there? Let me What do I get? Well, very simply, b minus lambda times a du dy. And that's the same as minus a times du dx along the curve plus c. And I have introduced now an abbreviation, namely this lambda is dy dx along f. And in some sense, this corresponds to the slope of f. I call this equation number 2, this equation number 3. Okay. So far, I think everything I did was basic manipulations, so nothing really strange. But of course, at the same time, you also have not learned anything yet. We have just done some manipulations. But we can maybe amend our sketch a little bit. So first of all, I have the slope of my curve, which is this lambda. So this here is lambda, which is dy dx along f. And of course, now what you see here is that this lambda is actually not dependent on the solution. It is entirely a geometrical result based on the curve S that I have chosen. But what I have also, what I can also indicate in this plot, and of course it's not so straightforward to do that, but I have now two different derivatives. I have the derivative du dx, and I have the derivative du dy. Du dx is the total derivative, and du dy is a partial derivative. So in some sense, I can write that I have a derivative here. That's the derivative of the solution in the y direction, and then I have kind of the derivative du dx, the total derivative that is in the direction of the curve. This is du dx along the curve. So I have two different. So I have a slope. I have two different derivatives, one along the curve and the other one in the y direction, a partial derivative in the y direction. And I have a relation between them, as indicated by equation number 2. Okay, with this, I guess we can also close the first hour of today, and we can have 15 minutes of break, and we just continue at 15:15 with kind of making sense of this, what I have written down. So I will stop the recording or pause the recording. Okay, so welcome back. And what we just, or what we finished before the break was writing up this equation system number 2. And we discussed very briefly in this sketch what it actually means. It means that equation 2 relates the derivative along the curve with the derivative in the y direction. Well, why is this important, or why could this actually, lead to something? Well, now what we're doing is we look now for specific curves f, for which the evolution of u along f, so the evolution of u along the curve f, so essentially that is the knowledge of du dx along the curve f, is not enough, or it's not sufficient to determine the complete u. And the complete u, I would now say that's du dy. So the derivative in the vertical direction, which is not along the curve. Or in other words, or simply, I look for specific curves for which knowing du dx along f is not enough to compute du dy. So, well, again, just to kind of indicate this in the sketch, what I say is knowing, I look for curves f where knowing the evolution along the curve is not enough to calculate the derivative in the vertical direction. As simple as that. Okay, how can we translate this into mathematical language? So I'm saying I'm looking for curves where knowing du dx, so specific curves where knowing du dx is not enough to calculate du dy. Well, what does that mean in terms of the mathematical formulation? Well, it means that I cannot solve this system. I cannot multiply this guy to the right side. Okay, because if I can, then I can invert b minus lambda a, and I can calculate du dy. But now I'm looking for the ones where this is not possible. Well, where is it not? Or what is the condition that this is not possible? Well, the condition is from equation 2, it means that b minus lambda a is singular. So b minus lambda a is singular. That's when I cannot calculate du dy. Of course, this translates into determinant of b minus lambda a is equaling 0. Or, that's maybe the easiest way to understand it, lambda is an eigenvalue of the generalized eigenvalue problem b times a equaling lambda a, where lambda is the eigenvalue and a would be the eigenvectors. Okay, kind of do you get the point here with this geometrical interpretation of going from one derivative to the other? Okay, so now we have a way of calculating these very special curves based on the matrices A and B. Essentially, we just need to solve an eigenvalue problem. Now it turns out that these curves f, they actually have a specific name. So these curves with lambda being dy over dx, these are called the characteristics of the original system 1. So what we have done here is we have calculated the so-called characteristics of the original system. And I know in the literature, also in other courses, there is different ways of calculating these characteristics. The way that I chose here is, in my view, kind of how should I say, it's an intuitive way of understanding why the characteristics actually look like, or why they're calculated in the way that they are calculated. There's different ways, of course, of doing that, but I particularly like this way. Now we have calculated the characteristics as these eigenvalues, but the question now is, okay, what can we do with that? Well, it turns out that the importance with the characteristics is that the solution may actually change in a discontinuous way when it goes over the characteristics. There's no flow of information over the characteristics. All the information flows along the characteristics, so flows along this curve f that I was saying. But the whole point with the characteristics is that there's no flow of information across the characteristics. That's exactly, this that it's inhibited to go across is exactly expressed in this equation here, that it is not flowing over across the characteristics. So that means the solution may be discontinuous over the characteristics. It doesn't have to be, but it may be. But along the characteristics, so that means the curve f, typically a simpler equation, holds. Because that's exactly the direction in which the information flows, and because these curves f's are very specific for a particular problem. Typically, one can reduce the order of the system, or going from partial to an ordinary differential equation along the characteristics once you know how they look like. And this is actually something that we will look at later on, but it's also known as the method of characteristics. To solve these type of equations. It will also come back when we talk about Riemann invariants or characteristic boundary conditions, which you may have seen in certain applications. So it's all about, so the characteristics is all about the directions in which the information flows. And that's kind of the important point here. But now, depending on the number of eigenvalues and the type of the eigenvectors of these characteristics, we can actually do our type classification that we wanted to do. So that's definition number 2. So depending on the eigenvalue in equation number 4, we call the type of the original system 1 as follows. And I guess now you will kind of understand what I meant with type. Well, A would be hyperbolic, hyperbolic type. Hyperbolic, and that is the case if we have n eigenvalues, n real eigenvalues, that's the whole point, n real eigenvalues, and n linearly independent eigenvectors A. So if we do this calculation and we find that we have n real eigenvalues and n linearly independent eigenvectors, then we deal with a hyperbolic problem. And in a second, we will start to look at model problems, or one specific model problem for hyperbolic problems, for hyperbolic equations, to also see what it means in practice to have a real eigenvalue. The second type that we would like to look at is parabolic, and that is if we have n real eigenvalues, but less than n independent, linearly independent eigenvectors. So if you have some eigenvectors that are the same or linearly dependent, then we are not talking about a hyperbolic, but rather a parabolic problem. But yet all the eigenvalues are still real. And then we have the third one, and that is elliptic. And an elliptic problem is then if we have n complex eigenvalues. And with complex, I mean non-real. I mean, we have a non-zero imaginary part. Then we talk about elliptic problem. And of course, the world is not always so easy. So there is also something that's called a mixed type. And that is typically the case when we have both real and complex eigenvalues. Real and complex eigenvalues. But even if the equation is of mixed type, you can still identify certain aspects of the solution that have kind of a hyperbolic character, other parts that have a parabolic or elliptic character. And we will see that also when we start to talk about Navier-Stokes, because the Navier-Stokes equations, they are essentially parabolic equations, but they have aspects of hyperbolic equations when it comes about the convective part, but also the pressure equation, which then will turn out to be a Poisson equation, which is an elliptic problem. So they combine both of these aspects together. So it's even in the mixed case, it's important to kind of know what types or what the eigenvalue, what the characteristics really are. Okay, let's do an example, because this was all a little bit theoretical. But let's just do a simple example here to understand what we actually mean with all of this. So since we're doing fluid mechanics, I chose an example from fluid mechanics, and that is the Prandtl-Glauert equation. That is an equation, I forgot now from what year it is, probably in the 20s, 30s, and it describes the two-dimensional, inviscid, linearized and compressible flow over a thin body. I mean, you can think of a rocket, for instance. So you have something like this, a very thin body like this, and it describes the flow kind of around this, and it describes how the kind of the flow is deflected in this case. The equation is as follows. It's 1 minus Mach infinity, or well, let's call it m infinity to the power of 2 times d squared phi dx squared plus d squared phi dy squared equaling 0. And so the parameters that we have in here, so we have m infinity, that's the Mach number in the free stream. In the free stream. So that means, I mean, if I have the free stream here, so I have u infinity here, and then the Mach number obviously is, it's u infinity divided by the speed of sound c infinity, I can say. So that would be the Mach number, and then the phi here is the velocity potential. The velocity potential that's one way of writing the velocity field as a scalar. Essentially, it means that u, so the x velocity, would then be the x derivative of this phi, and v would be the y derivative of this phi. So that's the velocity potential. So this here is the Prandtl-Mach, the Prandtl-Glauert equation, and as I said, it's typically used for rockets and things like that. But now what we want to do is, we don't want to solve it, but we would rather like to determine the type of this equation. Now, we see already one problem right from the start, namely that this equation is of second order, not of first order as we did the derivation, but the rest is okay. I mean, it's linear, it's in two variables, x and y, so everything else is kind of okay. But somehow we need to rewrite the equation such that it becomes first order. Of course, that's already the first trick. So we need to rewrite it as a system of first order partial differential equations. And for that, of course, we directly use the definition of the velocity potential, namely that we have exactly this relation that u is the derivative in x and then the v is the derivative in y. Now just plug that into the equation, and then what I get is the following. I write it down and then we can briefly discuss about it. So I have 1 minus the Mach number squared times ux plus vx is 0, and the second equation is uy minus vx is 0. Okay, so what did we write here? So the first line here, that's essentially the Prandtl-Glauert equation. So the second derivative of phi with respect to x is of course the first derivative of u, and then here we have the second derivative in terms of y is the this of course should be that should be a y here, of course. So, okay, that should be a y. So the first line here is the actual equation, and then the second line uy minus vx. That's kind of the compatibility condition, which comes from the fact that phi xy is the same as phi yx. And that is called the equation is called the equality of the mixed partials in English. I guess it's also known as the theorem of Schwarz in certain countries. But I guess, this is always, you can switch the derivatives as you like. Okay, so now we have this this system here, and now we would like to now we're in the situation that we have a linear equation and it's first order. So now we can just go into our recipe that we derived during the last hour and determine the type. Now, to put it into the language of before, I can introduce the vector u, which in this case would just be u and v. I can define the matrix A, which would be 1 minus the Mach number squared, 0, 0, minus 1. And B would then be 0, 1, 1, 0. Okay, so these are now U, B, and A. And now I just need to solve the eigenvalue problem that I have written up before, namely this one here. B times A is lambda AA. And then once I have solved it, I need to look at the eigenvalues and eigenvectors and then determine whether a system is, whether the system is hyperbolic or whatever. Now, to make it a little bit simpler, I directly calculate, or I write down the solution for the eigenvalues and eigenvectors. Of course, you can look at, you can redo this calculation. What I get is the following. So for the eigenvalues, I get the following. Plus minus the square root of m squared minus 1 up to the minus 1. And for the eigenvectors, I get an eigenvector which looks like this, 1 in x, and then minus plus the square root of m infinity squared minus 1. So this is now these are the eigenvalues and eigenvectors. And now the question is, okay, what is the type of this equation? Obviously, you can see here that it depends on the Mach number. So depending on whether the Mach number is larger than 1 or lower than 1, you know, the argument in the square root is either positive or negative. And as you know, if you have a negative argument in the square root, you will get a complex number or an imaginary number. And if it's positive, you will get a real number. So that means what we can directly see is if we want to get a complex number for lambda, Mach needs to be lower than 1. And that's, I guess, easily to see. If m infinity is lower 1, then we will get lambda 1 and 2 are complex, or non-real, as I was saying before. And of course, that means we'll get an elliptic behavior. If the Mach number is exactly 1, then we will get 0 here, which is technically speaking a real number. I mean, in the square root, then we have them up to the -1, which of course complicates things a little bit, but we will get back to that. Having a 0 here essentially just means that that you get a vertical slope here. And for the eigenvector, it means again that you will get a 0, but it means that you have two linearly dependent eigenvectors. So what you get is lambda 1, 2 are real, but a 1, 2 are linearly dependent. And that means I'll get a parabolic problem. And similarly, if we're at the other side, if Mach is larger than 1, then we have again lambda 1 and 2 are real, but a1 and 2, they are linearly independent. And of course, this we can easily see in the bracket here. If it's larger than 1, we just get two numbers here, and of course, this is a linearly independent vector. In this case, then we have a hyperbolic problem. Okay, yeah, what is now the physical meaning of that? I guess it's not surprising that the type actually depends on the Mach number, because that's what we already said before. If you are at a low Mach number flow, typically you would not expect discontinuities to happen in the flow. And that's exactly what you see here. If Mach is lower than 0, lower than 1, then you're of elliptic type. And elliptic is kind of, Poisson type of solutions. And as soon as the Mach number is larger than 1, then you're in the regime of hyperbolic equations where shocks and these type of bad things may happen. I mean, essentially it means for Mach lower than 1, then we are in a subsonic regime. And if we're higher than 1, we're at a supersonic regime. And of course, in the middle, you can say it's kind of a transonic regime. But now the nice thing is also we can go even further with the physical interpretation of all of this. So we can really try to understand from a physical point of view how this change of mathematical properties actually happens. Now, in the language of Prandtl and Glauert, we can then define an angle, gamma in this case, which would be 1 over the Mach number. And then it turns out that this lambda 1 and 2, so these eigenvectors that we calculated, that would correspond to, I mean, as we wrote above, this is this Mach number squared minus 1 up to the -1. And actually, this is the slope, and this, of course, then relates to the tangent of this mu, as a slope typically does. Now, sketching this, looks like the following. So if you have the x direction and the y direction, then we can draw in kind of two lines with plus minus gamma. Not gamma, mu, of course. And from these equations, we can now see that it's exactly these lines that are the characteristics. So these are the lines that are essentially defined with the sign of this mu being 1 over the Mach number. And in the language, or the kind of the physical language, these would not be the characteristics, but these are the so-called Mach lines. And now, if you think of you know, kind of supersonic flight and all these things, these would be the shock waves that are emanated from kind of an airplane or a body that is located at this point. And of course, this is then in some sense related to the sonic boom that you get whenever you exceed Mach 1. And now you can also understand perhaps a little bit what the relevant, or how in a physical way, how this changeover from hyperbolic to elliptic actually happens. So one thing you can see, that if you increase the speed, so if you're faster and faster, that means your Mach number goes up, it goes higher and higher. That means that the 1 over Mach is getting lower and lower, which then means that the sign of mu being lower and lower means that the angle is going lower and lower. So now the lower mu is, the higher the speed. So we can kind of say that it happens in this way, that the Mach number goes up, right? But that, of course, also means that at some point, so if you go in the other direction, the Mach number goes lower and lower. At some point, you will reach 90 degrees with mu. And that, of course, is reached if the Mach number is 1. So then the Mach lines are vertical. And of course, that exactly corresponds to the fact when the slope becomes infinity. But then what happens afterwards? Can you know, when the slope is vertical, or when the Mach lines are vertical, can they get, you know, more vertical than vertical? Obviously they cannot, and the Mach lines also cannot, you know, go forward. So that's why at that point, when you are vertical, and you decrease the speed even more, then it turns out that the Mach lines disappear, and the problem goes from hyperbolic into an elliptic problem. So physically, we can directly understand that there must happen something at Mach being 1. Okay, so this example, I think, is quite a nice one, because it really connects the mathematics to the physics and the expectations that we also have to the physical problem. And one can say this is a typical problem, a typical example where the type actually changes as a function of parameters, which actually may even change locally in your solution. So this is a typical example of equation which changes type as a function of possibly local parameters. You know, locally it may be so that the Mach number is larger than 1, and then suddenly you have kind of a region where the flow has clearly hyperbolic behavior. And as I was saying, it's knowing this determines what type of solution methods you would be choosing. Yeah, maybe one additional note I can make, and I can say that this was a steady problem, but if we were looking at the time-dependent problem, the corresponding time-dependent problem is always hyperbolic. So it also depends on whether we look at a steady or a hyperbolic problem. Okay, now having discussed the different types of that we can get, what we now should do as the next step is to discuss the different or model or the expected behavior for elliptic, parabolic, and elliptic equations. And this is what I would like to do next, to kind of introduce a number of model problems for each of those types and kind of understand how the solution is expected to look like, and also then later on use that as a tool to determine what numerical method may be suitable. And I guess we just go through cases A to C and look at them one in a row, one after the other. And I typically start with elliptic problems. I do that because it's kind of well, in some sense, it's the nicest problem when it comes to the analysis, but it's maybe also the most complicated problem when it comes to actually calculating that. So what are elliptic problems? These are typically steady diffusion problems or processes. When it comes to, because it's steady, it would kind of be it would be immediate interaction between all points. So that means there's no clear direction in which the solution would propagate. And that would mean there is no marching solution. You know, that something would kind of propagate from one direction to the other. Everything is instantaneous. The typical example for that is the Poisson equation or Laplace equation if the forcing is 0. So something like this: d squared u dx squared plus d squared u dy squared being 0. So this is kind of the typical problem that you would like to, or that you solve with the help of, or that is an elliptic problem. As I said, now of course I wrote it the wrong way. It should be f here if we talk about the Poisson equation, but it would be 0 if we would talk about the Laplace problem. Now, when it comes to boundary conditions, so if you look here at the domain and we have a point P here, as I was saying, it's important to realize that everything is instantaneous and everything depends on everything. So that means in order to be able to solve an elliptic problem, you need to have information of the boundary conditions everywhere, and essentially you need to solve everything at once. So boundary conditions are needed everywhere around the domain. Which I guess is an excellent time. So I can just define here, this is so if this is the domain G, and then we have the boundary delta G. So I guess this is an excellent time also to briefly talk about boundary conditions and the different types of boundary conditions that we use in CFD. Maybe the most classical boundary condition would be the Dirichlet boundary condition. The Dirichlet boundary condition essentially states that the solution at the boundary is given as a specific function, maybe g1 of x and y. So this is the most classical boundary condition. Think of a no-slip boundary condition. That would be a homogeneous Dirichlet boundary condition. There is also something that's called the Neumann boundary condition. Here it's important to realize that this is a Neumann boundary condition and not a von Neumann boundary condition. Von Neumann we will meet later on in the course when we talk about stability. These are two different people. Neumann was a physicist in the 18th century, and von Neumann was a computer scientist or mathematician in the 20th century. So the Neumann boundary condition is similar as the Dirichlet one, but it just, instead of setting the function value, it sets the derivative. So du dn around the boundary is then set to another function, x and y, g2 of x and y. And the third type is the so-called Robin, or actually it's a French guy, so it's a Robin boundary condition. Which is the combination of the Neumann and the Dirichlet boundary condition, in a sense that it's the sum of the derivative, so du dn, plus some coefficient times u along the boundary is given by another scalar function, g3. So these three conditions, so Dirichlet, Neumann, and Robin, these constitute the basic types of boundary conditions that one can have. There was a question: is the Neumann boundary condition same as a zero gradient boundary condition? Yes. Yeah. Yes. So a homogeneous. So a homogeneous Neumann condition would essentially mean that du dn is 0. So in that sense, you can say that this is a zero gradient boundary condition. But one needs to be a bit careful here, because sometimes in CFD codes with zero gradients or even stress-free boundary conditions, a slightly different thing is meant. Then it's typically the sum of the normal stresses that are 0. And the normal stresses are the pressure plus the velocity gradients. But typically, yes, I would say yes, it would be a gradient boundary condition. That's a homogeneous Neumann condition. And the no-slip boundary condition is a homogeneous Dirichlet condition. Okay, and as I said here now, for elliptic problems, for them to be well posed, and that's kind of the reason why we also introduced the well-posedness in the beginning. For these problems to be well posed, you need to have the solution to be continuously dependent on the boundary conditions, and that means that you need to have the boundary conditions at the right place. And for these problems, it means we need to have boundary conditions everywhere along the whole surface. Typically, you could combine Dirichlet and Neumann conditions in whatever way you want. There is some aspects that one needs to be a little bit careful about, in particular when you only have Neumann conditions. So there is some aspects of compatibility conditions for the case when you only have Neumann conditions. This is written in more detail in the script. I will not do it now in the lecture, but if you want, you can look it up there. But if you kind of do that, and we talk now very briefly about the expected behavior, it actually turns out that solutions to elliptic problems are what we would call well-behaved solutions. And well-behaved means that they are typically smooth solutions. It actually turns out that the solution is smoother than the forcing the forcing F that you have. And of course, the reason for that is because if you look here at this, if you have F here, then it's the second derivative, which is F. So you need to integrate it twice, essentially, to get to the solution. And of course, an integration can always be viewed as a process where you smoothen out things. A derivative, always makes things much more pointy, but then integration is smoothing out. So therefore, solutions to elliptic equations are well behaved, they're very smooth, but they're difficult to or costly to obtain. And that's exactly what I said before. Everything depends on everything. You don't have a propagation direction. Therefore, you need to solve for all points at once, meaning that you will, in most cases, you will end up with one system of equations which relates all the points with each other. And of course, that's a very big system to invert and solve. We will find some iterative ways or discuss some iterative ways in iterative solutions. Well, let's do like this. This is very expensive to solve everything at once. So expensive. But there's iterative solutions possible, which make it a little bit cheaper to solve these problems. And this is something that we look at in homework number 6, where we look at a Gauss-Seidel implementation. And also in the project, actually, we will need to solve these type of problems. Now, I realize that in 2 minutes it's 5 o'clock, and then we should stop. Let me just make one last comment, which kind of connects back to the idea that we had with the characteristics. When we talked about the characteristics, I was saying that the characteristics, they are kind of the directions in which the flow, the information flows. So that gives you a natural, propagation direction. And of course, the reason why in elliptic problems you don't have that direction and you need to solve for everything at once is because your characteristics are actually complex. So these characteristics, they are not directions in physical space, so not in x and y, but they're rather complex. So that means that the mathematical properties, they say that there are no physical propagation directions. And of course, that's exactly what happens in the end. Okay, with this, I guess I will have to close for today. And I don't remember when we see it. I think we see each other tomorrow again. And then we will continue to talk about hyperbolic and parabolic equations. So thanks a lot for today. I will now stop the recording.